Good morning, and thank you for joining us. Today's webinar is on Does Size Matter? Taking the mystery out of static Headspace file selection. Roger Bardsley, our applications chemist, is presenting. We will be taking questions. You can submit them throughout the presentation, and we will address them at the end. Okay, Roger, I'm going to turn it over to you.
Thank you, Shelley. Good morning, everybody. Webinar today that we're going to be talking about is Does Size Matter? Taking the mystery out of static Headspace file selection. I'm Roger Bardsley, an applications chemist with Teledyne Tekmar for the last 9 years. Today's webinar is going to focus on what Headspace instruments does Teledyne Tekmar offer. We have the HT3 and the Versa. We'll talk a little bit about vial size, and then we'll move into the Headspace theory. We'll look at the mass balance equation, partition coefficients, and the phase ratio. Then we'll get to the nitty-gritty aspects of the vial size. The HT3 is a valve and loop system for static Headspace. It has a 1 mil loop is standard. Other loop sizes are available for the customer to install. It has a 60 sample auto sampler, which allows at least 60 samples to run. If you have more than 60, the software allows you to continue past 60. Of course, you're going to have a chemist or app person there to add the more samples as samples get ran. It also has a 10-position sample pattern, which allows overlapping of samples. That is in case you have a 30-minute equilibration time for your Headspace vial and maybe a 10-minute GC run time. You can have samples ready every 10 minutes after the first vial is injected. Samples can be heated up to 300 degrees C. It does have a mass flow controller, which allows you to regulate the flow of the gas, not just the pressure of the gas, which allows it to have the dynamic trapping option where you can actually trap materials like you would in a purge and trap, except you would just sweep the Headspace, not the sample. You can run a loop and trap method at the same time in a sequence with this software. The Versa has a smaller footprint. It's literally 1 foot wide. It's static only. It has a 1 mil loop as a standard, and again, other loop sizes are available for the customer to install. It has a 20 sample auto sampler, but the software allows you to go past 20. There again, somebody would have to change out samples once the samples run. The sample heating, though, on this one only goes up to 200 degrees C. First question of the day I have for everybody is on your current Headspace applications. Teledyne means power through communication, so we'd like to hear from you what some of your applications are. Go ahead and you should see the poll if you can go ahead and select those. I'll let everybody select those. We're getting some good responses on them. For the ones that say other, could you please put your application in a question so we can see what the other is. Okay, so I'm going to go ahead and close the poll. Thank you for doing this. And I'm going to share it with you. As you can see, 76% are doing environmental, 6% pharmaceutical, 6% forensics, 12% of you are doing polymers, 24% are doing others. So if you could, the others, kind of let us know what the others may involve. Would help us out a little bit. Thanks for your participation. Moving on. We have 3 available sizes for our Headspace instruments. 22 mil, which is a lot of manufacturers call it a 20 mil vial, and that's because in the vial, when you manufacture a vial, you always leave a little bit of Headspace up there for overfill. Of course, if you measure the actual volume, it is 22 mils. We also have a 12 mil vial and a 9 mil vial. Behind the 12 and the 9 mil vial, you'll see the vial inserts that can be used for either of those. The vial has a narrower body and allows it to sit down in that sleeve, yet the top uses the same cap as a 22 mil vial. And when you assemble those, as you can see, they're all the same height. So the HT3 doesn't need any special sensors to figure out which height the vial is. So this comes up to question number 2. What size of vials are you typically using? The 22 mil, go ahead and vote for these, please. So we kind of understand, is anybody using some of these other sizes? I'll give you a couple more minutes here. Looks like everybody's completed. Thank you for voting. And I'll go ahead and share those results. Most people are using the 22 mil vial, and some are using the 12, but nobody's using the 9 mil vial. Again, thank you for assisting us on this. Okay, so does vial size matter? What we're going to look at is we're going to take a look at the mass balance equation, partition coefficient, and then the phase ratio. Then we'll get down to the nitty-gritty of vial size and look at some real data. The mass balance equation is the mass in the original sample is equal, when you put it in a headspace, will be equal to the mass in the gas volume versus the mass in the matrix, which again is the original volume that you put in there. If it's water, you're still going to have 5 mils of water when you equilibrate that headspace vial. So the mass in the original can be considered as the concentration of the original times the volume of the original or the matrix. The mass in the gas could be the concentration in the gas times the volume of the gas. And again, the mass in the matrix is equal to the concentration in the matrix times the volume of the matrix. Partition coefficient is equal to the concentration in the matrix divided by the concentration in the gas. Or another way to look at it is the concentration in the matrix is equal to the partition coefficient times the concentration of the gas. An interesting thing here is to keep in mind throughout our talk is a lower K value will result in higher headspace concentrations of the sample. So let's look at some partition coefficients. From the HT3 manual, we have this table in there. It was done, these organics in water at 50 degrees. Hexane has a partition coefficient about 0.015, benzene 2.5, toluene 2.1, xylene 1.3, and as you get more polar compounds, they have a higher partition coefficient. So if we solve for the original concentration epsilon O, we substitute in the values for those concentrations into that equation. Then we add in the partition coefficient over here. We get this equation. Solving for C, the concentration in the original, C sub O, you get C sub O is equal to the concentration of the gas phase times the value of the volume of the gas over the volume of the matrix plus the partition coefficient. The VG over VM is the phase ratio that we're talking about today. And again, looking at the equation, when K is very large, the phase ratio really won't matter at that point. So for your polars, the phase ratio won't be that critical. Now, let's look at the phase ratio that's available for the 3 different sizes of vials that we have. What we did, we have the 9 mil, the 12 mil, and the 22 mil vial. Put 1 mil in, 2 mils, 5 mils. For the 22 mil vial only, we put in 10 and 15 mils. You'll see here I say no. If you first can get 10 mils in a 9 mil vial, that kind of overgoes one of the laws of physics, I think. In a 12 mil vial, if you do put more than the 8 mils that is allowed in a 12 mil vial, what will happen is you will actually push that water up through the system, through the valves, and it'll come out the vent. That's why no, we don't want to flood the HT3 because that'll cause a very expensive repair. So as you can see over here on the left, I have placed the maximum liquid levels in the vials. So the 22 mil, we can go up to 17 mils. 12 mils, 8 mils is about the maximum. And a 9 mil vial, 5 mils is the maximum. So what are these phase ratios? For 1 mil of sample in a 9 mil vial, the phase ratio is 8. 2 mils is 3.5. 5 mils is 0.8. On a 12 mil vial, the phase ratios are 11, 5, and 1.4. And if you would put 8 mils in a 12 mil vial, the phase ratio would be 0.5, but I didn't do that for this experiment. 22 mil vial, the phase ratio for 1 mils is 21. Again, 2 is 10, 5 is 3.4, 10 mils is 1.2, And when you put in 15 mils, the phase ratio drops down to about less than 0.5, which is 0.466. So let's move on to the data itself. For the vial size study, we took a stock that was prepared of a VPH standard in water, used that same concentration for all the different vials. The compounds that were in there, you can see listed here, anywhere from pentane to the methyl naphthalenes. We do have a few polar compounds in there with the methyl tert butyl ether. The GC parameters we used were a 502 column, 30 meter, about 1 mil per minute helium flow with a split of 30:1. Inlet temperatures, we used a VPH oven program of 50 degrees. We also used the mass spec with the turbo pump. We did scan from 35 to 250 mass hertz, or mass units. And then the start time we had at about 2.5 minutes. For the HT3 itself, these are the parameters we used. And again, to mimic what we did in our manual, we set the platinum sample temperature at 50 degrees. This is what the chromatogram looked like. Very good peak separation, very nice sharp peaks. So let's look at the data. But how? What we chose to do was take a look at the function of a single volume in 3 different vials. So we compared that for the 1, 2, and 5 mils. Again, we couldn't do the 10 and 15 in the smaller vials, so we're just looking right now at those 3. Then we'll take a look at the function as a phase ratio. We'll do it uncorrected. Uncorrected would be if you have a lot of sample, how much can you put in there and truly see? If you have a minimum sample value, though, what I did was also correct that same data for the volume. So I took the 15 mils that I may have put in the 22 mil vial and divided that peak area by 15 to bring everything down to the same concentration. So looking at the phase ratio at 50 degrees, 1 mil sample in the 9 mil vial I set as 100%. So I divided all of the other compounds by that 100%. So I made that 1 mil sample in the 9 mil vial of 100, and then we compared the 12 mil vial over here and the 22 mil vial over here. Their phase ratios for the 1 mil and 9 mil is 8, where the phase ratio for the 1 mil in the 12 mil vial is 11, and for the 22 mil vial it's 21. So I included the phase ratio here. And as you can see, not a lot of difference when you do 1 mil and a 12 mil vial, but a significant difference when you do 1 mil in a 22 mil vial. MTB is the second peak here. As you can see, it's significantly different than some of the other peaks. Also looking out here at the undecane naphthalene and the 2-methylnaphthalenes, they're starting to show a little bit of non-difference in that. So there may be a little bit of polarity there too, or a larger partition coefficient. Now looking at 2 mil sample in a 9 mil vial, again is 100%, phase ratio of 3.5. Phase ratio of the 2 mils in the 12 mil vial is 5, and the phase ratio of 2 mils in the 22 mil vial is 10. And here we can start seeing some pretty significant difference. MTB is starting to really stand out, along with a few of the others in the middle region of the chromatogram. Moving on to 5 mil samples in a 9 mil vial, doing the same thing. The phase ratio on the 9 mil vial is 0.8. The phase ratio on the 12 mil vial is 1.4, and the phase ratio on the 22 mil vial is 3.4. And again, we're starting to see some really significant differences in some of these compounds here. So to remember, phase ratio is the value Vg over Vm in the equation. And again, when the K is large, the phase ratio doesn't appear to matter. And we saw that with the MTBE and some of the later naphthalenes. So let's look at some of the different parameters. Separating these out and looking at phase ratio at 50 degrees for all these compounds, uncorrected. For the compounds that have a low K value, the pentane, the heptane, the dimethylpentane, cyclohexane, heptane. When we look at the phase ratios all the way from 0.4 down to 21, and I put over here the vial and the volume in the vial, you can see a significant difference in the phase ratios for these compounds that have a low K compound. So if I was doing a test that had a lot of compounds in it that had a low partition value, I may want to use 15 mils in a 22 mil vial if I have plenty of sample. Now, when I correct all those for the volume, so again, taking that 15 mil sample size, dividing that peak area by 15, I get this chart here. I still see that trend of the phase ratio is showing some difference here, but again, some of these peaks aren't as big. So looking at them separated out, taking the pentane, for example, which is the low K value, I see a significant difference based on the partition coefficient, or the phase ratio. So phase ratio of 0.8 will give me almost 3 times the amount of peak area versus a phase ratio of 8. And as you can see, when I correct for volume, that phase ratio of 0.46 in the 22 mil vial drops down. Cyclohexane shows a similar trend that we see this. And again, this is for a compound that has a very low partition coefficient. Moving on to some of the compounds that had the higher, what we felt was a higher K value, higher partition coefficient, the MTBE, the naphthalene, and the 2 methylnaphthalines at the end of the chromatogram. As we can see, we kind of see the same trend here for uncorrected. So if you have a large sample amount, 15 mils in the 22 mil vial would be the way to go. However, looking at it as the uncorrected values with the high K values and just focusing on these, separating that out, again, as I stated, the 15 mil samples in the 22 mil vial would be the better way to go. However, if you only have 5 mils of sample, you don't see a lot of difference here in the green bars, which is the 5 mils. So again, we're starting to see that with these higher K values, the phase ratio isn't as critical as with something with a lower K value. Naphthalene is kind of the same way. It almost has the same response for the same volume in the vial. But you can get a higher peak area by putting more sample into a larger vial. Again, with these higher K values, when I correct it for volume, we see a significant change here. Pulling out the MTBE again and the naphthalene, again, we see that for a 1 mil sample in the 9 mil vial, if that's all the sample I would have, it would be better to use a 9 mil vial over the 22 mil vial. But again, that with a higher partition coefficient, you don't get that significant increase that you see with the lower partition coefficient for the compounds in the peak area. Going from 400,000 area counts to 700,000 area counts isn't like what we saw before, where we saw a 3 to 4 time increase in that peak area. Same way with naphthalene for all 3 different volumes in there. Now let's look at some of the middle partition coefficient values. Again, we see the similar trend here. And this is uncorrected. This is if I put that much sample into the vial. Pulling out the benzene and the 4-isopropyl-toluene, again, we see a trend, but not as significant as we saw before. From 2 million to 8 million. Isn't that significant as what we saw with the compounds that had a lower partition coefficient? And there again, for these compounds, if we went to 15 mils, if we had that much sample to use, a 22 mil vial would be the better way to go. Now, let's correct those values again for the volume. We see a different chart here with some of the middle value partition coefficient values that we've seen. Again, pulling those out so we can see each one individually. With the benzene, we really don't see a large difference here in that peak area when it's corrected for volume. Okay? So again, as that equation changes, as our partition coefficient increases in value, we don't get that much more sensitivity. So, kind of wrapping up, for a 1 mil sample, if that's all you have, it's better to go with a 9 mil or 12 mil vial than a 22 mil vial for most of the compounds. A 5 mil sample, you're good to go with a 9 mil vial over a 12 mil vial or a 22 mil vial for compounds that have a low partition coefficient. If you have compounds that have a high partition coefficient, that vial size will not make a difference. So, does size matter? I think we've kind of taken some of the mystery out of the static headspace vial selection. We looked at partition coefficients. Partition coefficients are temperature dependent. So if I did this at 60, 70, or 80 degrees, I may expect to see a difference in some of these compounds because, again, that partition coefficient for those compounds will change. The phase ratio can be critical. Its greatest effect is on compounds with very low partition coefficients, but we really don't see a lot of effect on compounds with high partition coefficients. Again, if you have a limited sample volume, when you're doing your method development, you want to really take a look at the vial size to see, can I get a significant improvement in my detection of these compounds, or does it really not create that much of a difference? Also on polar compounds, really didn't talk about this at this point, but you can have a salting out effect that by putting a salt in there, you can change that phase ratio and break that attraction between the polar compound and the water to help salt those compounds out a little bit better. That'll be in possibly another webinar in the future. I'd like to thank everybody for coming today. At this point, we'll start to take some of your questions that you might have.